Let's dive into chapter 6.8 part 1, and just a reminder, before you plunge into part 1 you should do the organizer for common function limits and the chapter 6.8 warm-up assignment. Let's think back, way back toward the start of the semester. I gave you this application where we have a bacterial population growing at a particular rate that depends on time. That's a letter T. CFU here is a biological thing called colony forming units. That's one way to measure bacterial population. And we said at time 2 the population is 70, and how big is the population at time t? So try to write down an expression that will tell you the population at time t based on the population at time 2 being 70 and this growth rate function. So pause the video and do that. All right, welcome back. One way you could do it is say big F at big T. Well, we start at 70 at time 2, and then we integrate from t equals 2 to t equals big T r of t dt. So that's accumulating net change as time goes along. If you put in big T equals 2, then this is the integral from 2 to 2, which is 0, and then we just get 70, so that's good. And you can plug in this formula for r of t and take an antiderivative. That's not the issue right now. You end up getting something that starts here at 70 and looks kind of like that. And I asked a question there, and we didn't spend a lot of time on it. What happens as t goes to infinity? Is it going to infinity? Or will this level off? Will there be a horizontal asymptote? So that's a good question, but I accidentally made a mistake, maybe not accidentally, in asking. And the problem is I used the word it. The word it is your enemy in this chapter. So I want to circle the word it and cross off the word it and say, don't use it. The reason why is the word it is ambiguous. Does it mean this function? It's pretty clear here that that's what I meant by it. Or does it mean this function? So let's write that. So it is ambiguous. Are we talking about the original function, like the integrand? Are we talking about the integrated function? So you should be very clear when you're saying something is going to 0, something is going to infinity, what that something is. Are you talking about the integrand or the integrated function, the antiderivative? So that's our first big warning. All right, this has a yucky expression. It's going to involve logs when you take antiderivatives. Let's use a nicer version that's just simpler. Let's think about the integral from 0 to 1 e to the negative x dx. So go ahead and work on that. It's a good idea to sketch it, right? So it starts here, does something like that. And then what's the antiderivative? You could say this answer is negative e to the negative x from 0 to 1, which is negative e to the negative 1 minus e to the 0, which is minus e to the minus 1 minus 1. Remember, e to the 0 is not 0, it's 1. So this is negative, let's turn that to positive, 1 minus e to the minus 1, which is about 0.63-ish. In my family, when a baby reaches their 0.63-ish birthday, we have a very, very tiny party because this is a really common number in various types of math. So fairly straightforward. What does this integrand look like? So this was little f. As we're doing it as a function of t, this is growing like that. And we found out that by the time you get here, you get something like 0.63. And now the question is, what if I keep integrating longer, not just to 1, but to 10 and 100 and so forth? What happens to this function? So let's actually do that. Go ahead and do the integral 0 to 10 e to the negative x dx. Do you need to repeat all this stuff, or can you just write down basically what we did but replace the 1 with the 10, the 1 in the power? So that would be 1 minus e to the minus 10, which I'm going to abbreviate as 1 minus tiny. E to the minus 10 is pretty small. So let's say that's 0.999-ish. Let's try integrating 0 to 100. What would you get here? 1 minus e to the negative 100, which is 1 minus minuscule. I'm just making up tiny words here, which is going to be 0.9999999-ish. It'll stop with the 9s eventually. It doesn't really matter where at this point. So here's the big question. What would you say is the integral 0 to infinity e to the negative x dx? Well, based on this pattern, what would you write that as? You would write it as 1 minus e to the minus infinity. We should kind of put quotes around that because it's not exactly a proper math thing to say, but engineers tend to say that stuff like that anyway, and that's okay. So how would you write it here? Would you say that's basically 1 minus as small as you can get, smaller than minuscule, like infinitesimally small, like 0? So is that just 1? Does that seem like it would work? So we're saying that the area under this curve, the e to the minus x curve, from 0 all the way out to infinity, we're saying that that area, even though it goes on forever, is a finite number, and it's actually just the number 1. Does that seem a little counterintuitive? That's okay, that's kind of what we're in calculus to learn, right? So that this total area, even though you're integrating to infinity, the area is not infinite. So let's go to the next. Next we'll do an actual definition and then another practice problem.